Oh, hi, everyone. Welcome to Foundation of Computer Science again. So let's see. We only have, so we have a smaller number of attendants today. But I guess getting to the end of the semester, we are kind of tired, I guess. That's normal, but we still have something that we would like to talk about. So just get as much as you can, because what we have seen and what we are going to talk about is perhaps the most difficult proofs you have ever seen in this course, and most likely it's also the most difficult proofs that in your whole curriculum, in your whole undergraduate curriculum. So if you find it hard, and if you find it hard to look at this material, so that is not uncommon, because it took Turing Award winners to figure this out about 40 years ago. Of course, even though, because it would be easier for us to learn, but still, this is a kind of difficult subject. So just try to get as much as you can. And fortunately, of course, for your evaluation, you don't need to write your proofs. You just need to determine whether a given proof is correct or not, right? So that is a lot easier. So verification is a lot easier than finding a solution. And you know that, right? So that's the concept of NP completeness. So speaking of NP completeness, so let me refresh your memories, what we have done so far. So we start from the bounded halting problem. Well, so this bounded, sorry. So we started, the first NP complete problem we saw is bounded halting, which simply adds a time bound to the undecidable halting problem. So it comes from halting problem. Okay, and then we look at a bounded tiling problem, and we also call that Levin's theorem. Okay. After that, we reduce bounded tiling to satisfiability, SAT, and that is called Cook's theorem. Okay, and then we look at 3 SAT, and that is one of the results proven by Karp. So we could call it Karp theorem. Okay, so both of these two people, they are Turing Award winner. Of course, Nevin could have made Turing Award if he were in the US. He was in Russia then. Okay, of course, after that, I think in the late 1970s, Levin immigrated to the US. Now he is at BU. So this is some of the history. Levin is at BU, Cook is at Toronto, and Karp is at Berkeley. So they were the pioneers of NP completeness. So let's remember their contributions and their theorems we learned. And then from here, we use reduction. So we talk about polynomial time reduction or polynomial time mapping reduction. Sometimes we also call it a polynomial time many-to-one reduction. So from here, we know that what we do here is that we reduce bounded tiling. So we reduce bounded tiling to SAT, and then we reduce SAT to 3 SAT. Okay, so after that, we also look at a vertex cover problem. Okay, so that's 3 SAT is reduced to VC, vertex cover. And last time we looked at directed Hamiltonian path. Okay, so that is NP complete. So we also reduce 3 SAT to directed Hamiltonian path. So I think we call it, so bounded tiling is called BT, SAT satisfiability, and 3 SAT. So this is called Ham pass. So we reduced 3 SAT to hand pass. Okay, so that's what we have done so far. Now let's check whether I miss anything here. Okay, not this one. Not this one either. Is this one? No. This one. Yep. So hand pass we move back a little. So this is VC, vertex cover. And also we look at clique. So because the reductions we have looked at earlier, so I think this is a number 5 is actually clique. And number 6 is vertex cover, and number 7 is directed Hamiltonian path. So again, we also reduce 3SAT to clique. So that is what we did. Okay. All right. So this proof of reducing 3SAT to directed Hamiltonian path problem is perhaps the most difficult proof. Well, it is the most difficult one that we are going to see, and we have seen, and it's likely the most difficult proof in your entire undergraduate curriculum. So let's just go over a little bit again. So you may find it useful in the future if you go to grad school, even you go to work, if you have to ever need to prove some problem that's NP hard, so that you can tell your boss that nobody else can find an efficient algorithm, and that would be useful, right? So years ago, I saw a cartoon, and people say, why do you need to learn this stuff, right? It's NP completeness. Do I ever need to deal with NP complete hard problems? Well, the cartoon has the following picture. So the boss came to you and say, oh, hey, I have a problem here. Can you find an efficient algorithm? Right? So you develop software, you write code, but before you write code, you must have an algorithm. You must have figured out the algorithm. Okay, so your boss gave you a problem, and then you go back and then try to come up with an efficient algorithm and look at whatever you have learned from algorithms, and you couldn't find one. Okay, now you have two choices. One choice is you go to your boss and say, hey, I spent days and nights, sleepless nights, then I still couldn't find an efficient algorithm. Okay, so of course the implication then there is that you are not competent enough, right? Or the other choice is you show the problem you're given by your boss is NP hard, and then you can just bring it to your boss and say, hey, I prove that this problem is NP hard, hence there is no, hence it's unlikely that we can find and polynomial time algorithm for solving it, because many of the best brains in the world have tried solving NP complete problems and they failed, right? So then, of course, so this, of course, is a much better option than simply going to your boss and telling him or her that you couldn't find an efficient algorithm, right? So that, at least from some point of view, it explains the usefulness of at least knowing some of this stuff. The concept of NP completeness and what it means, and when it's needed, you can at least have a direction where to look for such things. Okay, so now let's refresh our mind that For some reason, I have to stop share and share it again. Okay, let's see this most difficult proof how it is done. So we are going to reduce 3SAT to directed Hamiltonian paths. So what it means here is that, let's say I have a formula which is in the form of 3CNF, okay, conjunctive normal form, which means that each clause has 3 literals. And let's say we have M clauses and we have N variables. Okay. N variables. So what we are going to construct, so we need to construct a graph. Construct a graph, and this graph has to be directed graph. And that graph has to, let me use this word, encode. So in other words, that graph somehow represents this formula such that this formula phi is positive, meaning it belongs to 3SAT. Positive means it is satisfiable. If and only if, let's put this G as the graph we're constructing, and also has 2 points. Okay, so you construct a G, you also specify 2 points S and T, because this is a path. So this path from S and T will go through every other nodes exactly once. Okay, so from S to T, but goes through every other nodes exactly once, every other nodes in G exactly once. So that means this phi is positive if and only if G has a Hamiltonian path from S to T. So then the construction of this directed graph, okay, is challenging. But of course, now we just need to verify the construction given in the textbook is correct. So our job is easier. And imagine how difficult it would be if you were the first one trying to come up with this construction. Okay, so now let's go to our slides here. Let me see, I can bring up the slides. No. Okay, so let me stop sharing and bring this up. Okay. Yeah, normally I would pre-record my lecture because that would be easier. But then some told me that perhaps it would be better to not to pre-record any video. So now let's see how we can bring this one up. Share. And bring this up. It doesn't show. Okay, so let me. Now it shows. Okay, so now let's look at our formula here. In the form, so in the form like this. So this, the first one is like cross C1, C2, CK. Okay, instead of M, we use K. So you have K crosses, and each cross you have 3 little rows, and the total number of variables is L. Okay, in here is L. I use M and N earlier. So let's say you have K crosses, you have L variables. So then the construction, it's in this a chain of diamond shape. Okay, so for each variable, we are going to come up with a shape like this. Okay, so this is really, so you have 4 boundary nodes like this. So this is a boundary, and then for each clauses, so for each clause, now you think about, you have a clause here, you have clause here. Okay, so then a pair of nodes represent a clause, and then each pair of nodes is separated by a separator. Okay. Okay, so it's like this. Okay. Okay, so now remember we have this here. Okay, like this for these diamonds. So these diamonds is connected. They are used to connect a chain of diamonds, and then each of these pair. So this is represent C1, and this is represent C2, and you have L of them. So that means now you got, sorry, you have K crosses. So so each so see, you have a separator for this, you have a separator for that. For the last one, you also have a separator. Okay, so let me just write it up so you can see this better. So I'm gonna write this here. I think it's better to use a whiteboard. Let's use a whiteboard here. Doesn't show. Start over. Okay, now it shows. All right. So let's look at xi. That's a variable. So what you're gonna have is a diamond shape. Let me make it very big. See this construction. Now, don't ask me how Cobb thought about this thing, because nobody really knows how he came up with this construction. All right, so we have a separator, and then we have a pair of nodes. So that is for C1, represents C1. So the edges, so then we have a separator, and this is for, so this for C1, this is for C2, and so on. So the last one, so I have a separator, and then I also have a separator at the end. So this is CL. Oh, CK, because we have K clauses. So that L is K. Let me change that. Okay. So then how do we connect these nodes? So the nodes, we connect them is like this. And so we can go from left to right. And we can also go from right to left. So that is for one variable. And you have, you look at the literals, right? So if the literals is like this, then you start the training. So the training looks like this. Okay, so let me go back to the slides. See whether you can see the slides here. Cannot. So stop it. Let's start this. Slides. So that's the chain. Okay, so we look at each of these guys. So we list S1 up to XL. The top of this is S. Okay, so now we go all the way down to T. So that is the graph G, a part of graph G, but now we still have to connect these guys. We still have make connection of these nodes. So now let's look at how these nodes are connected. Okay, so this is how we do this. And now remember here we have this is C1 up to CK, and we look at the pair of nodes in this diamond that represents CJ. And if Xi is in CJ, so CJ has 3 literals, and if it contains the original variable form, and then for that pair of nodes, you make this connection. So the left one goes to CJ, and CJ going to the right of that pair. All right, so now imagine each clause has 3 literals, so that's how you make all these connections. And if instead you have the complement of xi in Cj, so this would be xi instead of j, so this would be I here. Then you make an opposite connection. So then Cj will go to the left node of Cj pair. Now this pair of nodes for Cj, and then the right node going to Cj. So that's how we distinguish whether this is the original form of the variable in Cj or its complement in Cj. So that is the connection. So now I have connected all these nodes. And then, as you can see from here, okay, so now we have a better idea of this construction now. So what you're going to have, for instance, if, let's say, if x1 is in C1, then what you're going to have is, now this is a pair. This is a separator. So what you're going to have is this, and make that to the second. And if, let's say, x2 bar is in C1, right? Because C1 has 3 literals, then you do the second pair. Now, if I would complete this, I have a separator, and then this is the second pair. So what you do here is you go in here and go in there. Oh, I'm sorry, going to C1. So that's C1. So you go this, and then you go that, and then this is like that. Okay, so that's how you complete this graph. Now, if you draw the complete graph, that will look messy because there are a lot of lines here, but now you get the idea of what it looks like. And then what we are going to do here is that suppose phi is in 3 SAT. Okay, so that means that for each clause, there must be one literal that is set true. Okay, so now how can we come up with a path? Okay, so here we are going to do it like this. So we are going to say if xi is in Cj, then what we do is we go left first. Let's say if xi is in C1, then we go this way first. And then we travel like this, okay? And then we go there, going back, and then we keep traveling, and then go in here and go there. So that we go through every single node in the first diamond, and this direction is called zigzag. Okay, so likewise, if Ci bar is in Cj, then we go to the right, so we go zag. So that means now, for instance, for this C2 bar is in C1. So what we are doing here is that we go this way, and then we go here, and then we go there, and then we go there, and then we go down to the first one. Okay, so that means now I can go through every node. I can go through every single node in the first 2 diamonds exactly once, right? So then you just keep on doing until you get down to T. So that's how this Hamiltonian path is constructed. Okay, so let's see a description here. Okay, so that's what I just said. All right. So the zigzag here is that if xi, because xi appears in, if xi is assigned true, then we zigzag. If xi is assigned false, we zigzag. Okay, so essentially that's what I mean. So if xi, because for each variable here, it will appear in at least, right? So you have these clauses, and each variable will appear in a clause, and each clause is true because satisfiable. This formula is satisfiable. Then each clause is true, and then it has 3 literals. There must be at least 1 literal that is assigned true. Okay, the rest may be assigned true or maybe assigned false, but there must be at least 1 that's assigned true. So that one is literal. Then let's just look at whether it's in the original form of the variable or the complement of it, and then you know whether you pick zigzag or zigzag for that variable to work. Okay, so that's how we can come up with is a Hamiltonian path from S to T. So then the opposite is also true. If I have a Hamiltonian path to go from S, go through every other node exactly once down to T, then I can find a truth assignment to this variable. Okay. So for the reverse direction, right? So we can. So if the Hamiltonian path is normal, which means that if you look at the normal means you start from here, you go through each diamond in order, okay? Instead of jumping, so you come here, then you go to the next diamond. That's not normal. If it's normal, then it's easy to come up with a truth assignment for each of these variables to make the formula true. Otherwise, if it jumps, okay, from here to there, then we show that it's impossible, right? So this is where the cleverness comes in. So for this particular construction, so we can see here is that if we don't do the normal traversal, instead I go here, I go to this cross, and then I go to the next, not the immediate one, not the adjacent diamond. I go a diamond somewhere below, right? So it's not the adjacent diamond. Then this node will not be visited, because when you go here, then we can know that you have no way to go to this A2, because to go to A2, you will either go from A1 to A2, but A1 is already going there. So it can only come from A3, but here you don't really have a way to go to A3. Okay, so essentially that's the argument there. Okay, so as I said, I just want to give you some ideas about how difficult it could become by showing a problem is NP complete. But there's, as I said, you will not be asked to come up with a proof for a problem to be complete in your evaluation. You are presented with a proof. So you need to understand the concept of reduction and then verifies whether a given proof is correct or not. Okay, so that's an easier task than coming up with a proof. But we should see something more difficult, right? So that's the things that we saw. So next we're going to see another NP complete problem. So this is called undirected Hamiltonian path. So basically, is what we do is to get rid of this direction. So then obviously we are going to reduce Hamilton path to U Hamilton path. Now U means undirected here. So we are going to reduce Ham path to U Ham path. Okay. So that means that given a directed graph with two nodes S and T, I'm going to come up with, right? So I'm going to come up with another graph, G prime, which is undirected, and another node S prime and T prime, such that if there is a Hamiltonian path that starts from S, goes through every node in G exactly once and ends at T. If and only if there is a path that starts from S prime, goes through every node in G prime that ends at T prime, and this G prime has no direction. So then the idea is easier in this reduction, because what we are going to start is for each directed edge in G, we are going to use undirected graph to represent this edge. So what we do, let's call this U, and let's call this V. So what we are having is that for U, I have U in. I create three nodes, U in, so that's what we call it. U in, so that's one node. I have U mid, the middle, and I have U out. So what I'm going to connect is U in connects to U mid, and U mid connects to U out. So we sort of use this mid to indicate a direction. And then because it goes to V, so I have V in, I have V mid, middle point, and I have V out. So what I'm going to connect is that I connect U out to V in. And again, for V in connects to V mid, and V mid connects to V out. So for each edge, for each directed edge, U to V, I'm going to use this graph to represent, now this is undirected graph, to represent that edge. And then for X, I'm going to have X prime to be we call it S out. So this is always going out. And then T prime will just be T in, okay? And we don't have S mid, we don't have S in, we don't have T mid, we don't have T out. So that's what it is. So then we make, so you have a G, then I construct G prime. That's how I'm going to connect these things. Then you can see that if there is a path from S to T, goes through every node in G, then I can go through, I have a path starting from S prime, go through every node in here, and ends in Tn, right? So, and the opposite is also true because these two are, so this edge and that is equivalent. Okay, so that is this construction. So this is a lot easier. So let's say in the future, well, near future actually, if you either go to grad school or you either go to work, right? So you may at some point encounter such problems. Okay, so then you can the Hamiltonian path is NP complete. Then you can start from there instead of from let's say from way back like bounded tiling or 3S18. You don't have to. So you just come up with something that's already proven NP complete, and that looks very similar to your problem at hand. And if you cannot come up with a efficient algorithm, then the chances that this problem is NP complete are very high, right? So the nature is very interesting thing. So a lot of problems, they are either have polynomial time algorithms that we can find, or they are simply NP complete. Okay, so we have only seen a small number of problems that's sort of in between. We don't know whether it's in P, and also we don't know whether it's NP complete, right? So there are only a few problems in that category. So most of the problems, they are either in P or they are NP complete. So according to your textbook, we have one more problem that's NP complete. And after this, then we are done. So that is called the subset sum problem. So we know what subset sum is, right? So let me just start a whiteboard here. Okay. And let's go over this subset sum. Okay, so subset sum you are given is a set of numbers. Let's call it S. And so this S is a set of numbers, and also you are given a number T. So this is a given. So this is a set of numbers, and T here is a number. So what we want to know is that whether there is a subset ST S prime that's in S, there's a subset of S such that you sum up all the elements A in S prime. You just add them up. That's exactly equal to T. Okay, so that is subset sum problem. And then we're going to show that this problem is NP complete. Oops. Never know how it is. Okay. So what we are going to do is to reduce 3SAT to subset sum. So that means that we are going to now 3SAT, you are given a 3CNF formula that contains literals, and variables. So again, so let's say our formula, Boolean formula, consists of k clauses, C1 to Ck, and it consists of L variables. Okay, so then I'm going to use numbers to represent truth assignments, possible truth assignments. Okay, so this proof is also kind of hard. Okay, this is not straightforward. So let's spend some time to work this out. Okay, so this is what we're going to do. So we have these variables, and then for each variable, we're going to introduce a pair of variables. So for each xi, I'm going to introduce yi, zi to represent si, and then for each clause, so for each clause, I'm going to introduce two variables to represent that clause. So that's how it is. Okay, and then we are going to make a connection of this variable to numbers. So this is how we make it. Let's see this. Okay, now this is interesting because this encoding is kind of clever, but we do need to spend some time thinking about it. Okay, so we know that x1 is represented by y1 and z1. The reason I use two variables because I want to use one for its original form, the other one for its complement. Okay, so then for these, the numbers is just like this. Now we have L variables for x1. Y1, the value for Y1 is just 1, 0, 0, 0. So the value of Y1 is just 1, followed by L minus 1 zeros. Now this is in decimal, so this is a decimal number. This is a decimal number. Okay, likewise for Z1, I also use the same thing. And then Y2 will be 1, 0, L minus 2. Now, you see that? So this is this is L. This is for x2. So y2, you get this. Likewise, z2 is 1, 0, L2. Okay, so you go down. The last one is YL, which is now 1. And ZL is 1. So that's why you get down to this. So this is XL. So that's a number. But then I am going to put, so this is the first part of the number, and then there's a second part that is here. Okay, now this whole thing is a number. The whole thing here is a number. That means this number is not complete. So then I'm going to, so this time I'm going to make connection. So this K number, K digits here. So let me remove this. I have K digits here. That needs to be determined what it is. And now we have to make connection to the clause. So if Y1 appears in, so if X1 appears in C1, then I'm going to put 0, okay, in here. And then if, so because X1 is in C1, then X1 bar cannot be in C1, right? They cannot be in, if it's in a clause, that clause is, it's always true. So can only one can happen. So if that's 1, that's 0. If that's 0, this is 1, right? So that's how it is made. So that's how you make this connection. Now this represents example. So let's go back and see what this example is. Okay, so this example is this. So as I can see now, for X1 is represented by Y1 and Z1. So this is X1. And I know that the first part is 1 followed by L minus 1 zeros. So that's what it is. So this is decimal. And then X, now this is C1. This is C2. This is CK. So I know X1 is a C1. So that means now I put 1 here. And then X1 doesn't appear, assuming doesn't appear in any of these other guys. So then all of those are set 0 because it's not in C2. So I know that's 0. It's not in CK. Okay. And so I made that 0. And then you look at X1 bar. So X1 bar doesn't appear in 0. So that means that now doesn't appear in C1. So that's 0. It's not in C2, it's not in CK, so it's all zeros. And then we look at X2 here. So the first part is 1 followed by L minus 2 zeros right here. And then X2 bar is in C1. So that means that the bar is denoted by Z2. So this is 1 and this is 0. And then you look at C2, we know X2 is in C2, so that's why this is 1, and this is 0. Now look at the last one. So we know X3 bar is in CK. That means then, right here. So that means then this is in 3. Oh, so we didn't have 3 here, right? So Y3, so this is 3. So the last one, okay, so Z3 represent is X3 bar. So the last one here is 1. So that's this portion. And remember, I still have a second part of the variables that is G1H1, G2H2. Right, so let me clear this up. Okay, how do we assign their values? Okay, so we're gonna, if X1 appears in C1, then we make both of them 1, and X2 appears in C2, we make both of them 2. Okay, and we also know that So, well, actually, we just make them 1. Okay, so G1, H1 just 1, 1 on C1. Now, here, before that is all zeros. And G2, H2 make it to 1, 1, and so on. Now, the good thing here is that we can add them up. The first part, when we add them up, it's all ones. Because so in other words, this is my t. Okay, so I'm going to set t to be this number. So which means that now this is my s, right? So I have these numbers. I have these numbers. Now these are numbers, right? So I put all these numbers in s. Now, so these y1, z1 just for us to make connection to these numbers. But in s, it's just these numbers. And then I'm going to set t to be this number, 1. You have L1s, and then you have okay, I need to put L here. L1s and 3K. Now this is a decimal number. Decimal. Okay, so now what we want to do is to show that if this formula is satisfiable, then I can select these a subset S prime so that you add those numbers that's equal to T. Why? Because if each clause is true, okay, now remember we have K clauses and we have L variables, and if so these L variables, they all appear in one of the clause, right? So either itself or the complement of it is set to 1 because that's a truth assignment would do. So that means that any of these columns will have exactly 1 that's used because it's a truth assignment. So we can pick that number. And then for this, you may have more than 1, but I only need to select. Now we have 2 here already, but one of these will have to be, so one of these variable will have to be set true. So I can just pick that one, pick that number, okay? Whatever that number I pick, then I'm going to pick it. So that will make it 3. Okay, so that's how you can see that this formula is satisfiable if and only if there is a subset of S such that you sum them up the elements in that subset that's exactly equal to T. Okay, so you need some thinking, but you should be able to think it through. Okay, so that concludes chapter 7. Any question? I hope I didn't lose you too much. Well, this is hard stuff. Okay, it is hard, so I'm not saying that it's easy. It's challenging actually, but as I said, it's useful to know some of this stuff for your career, either you decide to go to grad school or you go to work. At some point, people will say, oh, if I go to work, I'm just writing code and people handed me the algorithm. Yeah, I mean, there are people, they will never see NP-complete problems in this field. But then, of course, they're just they are doing different things, right? So they don't have come up with algorithms. So if you ever need to come up with algorithms, you will have to deal with NP completeness sooner or later, because there are many problems that you cannot simply find. You cannot find the efficient algorithms. So as I said, if you cannot find it, your better way to do, okay, the better option for you is to show that the problem given to you is NP complete, so that you can you can show it to your boss or to your colleague and say, okay, hey, you cannot find an efficient algorithm to do it. Okay, it's very unlikely, right? So that is at least that is one of the purposes, so that you will not be looked as that you're not competent enough to find an efficient algorithm. Okay, so according to our plan, so we also need to talk about space-bounded computation, right? So this is time-bounded computation. We look at efficient algorithms, and for that we look for deterministic algorithms in polynomial time. So that's P. Okay, so that represents efficiency. And then we look at NP problems. So NP problems are problems that you can guess a solution, then verify that solution efficiently. However, how you find that solution may not be easy to do, but I can guess one and then I verified it. So as long as verification can be done efficiently, then it's NP. That's in NP. Then we want to know whether these problems in NP can be solved in polynomial time. So that's P versus NP problem. So that problem has been an open problem since 1960s, right? So this is 60 years ago, right? So people still struggle still struggling. So we don't know the answer at this time, even though we have developed a lot of theories and people prove a lot of theorems and about its properties over NP. So NP completeness is one of them. Okay, so that indicates that if a problem is NP complete, it is the hardest problem in NP. If that problem can be solved in P, then entire NP will collapse to P. Or if that problem cannot be solved by efficient algorithm, then we know P is not equal to NP. Okay, so next we're going to change is, again, we change to a new topic, which is Chapter 8, Space Complexity. Okay, so after this week, we have one more week of lecture. So we should be able to go through this 2 sets of slides. Okay, so let's look at this space complexity. We first look at definition, and okay, so it's sort of similar to defining time-bounded Turing machine. So we first defined space-bounded Turing machine. So let M be a Turing machine that holds on all inputs. And if this machine is non-deterministic, that means it holds on all branches of M, if M is non-deterministic. So because of it holds, then we can measure the space this computation takes. Okay, so the space complexity of M is the function f, where f of n is the maximum number of tape cells that M scans on any input of length n. So that basically you think about, I have a tape, I have a Turing machine, I have a tape. So the maximum number of cells that ever been used for this computation is the measure of space. And that is called the space complexity. Okay, so for the input x, right? And for different input x with the same length, for some x, you may use smaller number of cells, and for some other x, you may need a larger number of cells. So the maximum number of cells you ever need to use for an input of a length n is the space measure, okay, for inputs of a length n, and that's called f of n. So that's what this means. Now, likewise, similar to deterministic and non-deterministic times classes, we can also define deterministic space and non-deterministic space. So that's what it is. Space of f of n and n space f of n. So this is a non-deterministic space. This is space. Non-deterministic just means that you have non-deterministic Turing machines and you have to look at all branches. Okay, so now we define space f of n, which is a class of languages. Okay, languages itself is a set, which could also be infinite. So L here is a language decided by and big O of n, big O of f of n space deterministic Turing machine. And n space of f of n is the class of languages where this language is decided or accepted by and big O of f of n space non-deterministic Turing machine. So then, of course, we can see a few immediately things. So SAT is in space of n. Now it's deterministic. Well, it should be non-deterministic space. So because it's non-deterministic machines. Oops. Okay, so let's take a recess for 15 minutes, then we'll resume this topic at 8.